So now we want to talk about predicting the temperature range of spontaneity. So in addition to giving us, kind of this picture of does a process happen because of kind of the chemical bonds or the disorder aspects, one of the real reasons why we decompose delta G into the delta H and delta S components is because it lets us look at the temperature dependence of delta G, which means the temperature dependence of the spontaneousness of a chemical reaction. Generally, delta H and delta S, their values are pretty consistent with temperature. So delta G changes a lot with temperature because T is explicitly in there, right? I explicitly include the temperature in this calculation. And basically, we can see that the temperature is multiplied by the delta S. So at high temperature, delta S is going to be more important for determining delta G. So whatever the kind of entropy term is determining or kind of implying for how the spontaneousness of a reaction should be is going to be more important at high temperatures, whereas at low temperatures, delta H is going to be more important, right? If T is equal to 0, this would be just times 0, the delta S would go away, and all you'd care about is delta H. And so at infinitely high temperatures, the delta S is all that matters. And so there's kind of that temperature is explicitly in there. So delta H and delta S do not change much with temperature because it's really just like, it's a description of the kind of disorderedness or the strength of the chemical bonds. And that's fairly independent of temperature. But delta G is highly dependent on temperature. The T literally is in the equation. So we want to now explicitly look at the temperature dependence of delta G, which tells us the reaction spontaneity, how that changes with temperature. And we know that all that really matters is the sign of delta G. When does it change from being positive to negative or vice versa, right? Either direction. But no matter what, when the sign changes, delta G equals 0. So we can just plug in a 0 into our equation. We then do have to make an assumption that delta H and delta S don't change with temperature, which is a very good assumption, or pretty good. And then we end up with this equation that T is equal to delta H divided by delta S. This is the temperature where the spontaneousness would change, basically because the sign of delta G would change. It doesn't tell us if a reaction changes from being spontaneous to not spontaneous or anything like that, just that it will change. So if we kind of look over at our graph here, we're looking at the value of the free energy for a chemical reaction as you increase the temperature. And so the variability is based on the different signs of the enthalpy and entropy change. We said that for something that was exothermic, that increased spontaneity, that it was always spontaneous. And that's because we start out at a negative Gibbs free energy, and it just decreases. Conversely, endothermic reactions that decrease order, they start out at a positive Gibbs free energy and just go more positive, so getting further away from spontaneousness. So where it's interesting, where you can see a change in whether or not a reaction is spontaneous, is when the signs are the same. If you have an entropy-driven process, both were positive, right? It's an endothermic process, but delta S is also positive. So at low temperatures, the enthalpy term dominates. And because this thing was, you can see, entropy driven, at low temperatures, the non-favorable enthalpy dominates, and you're in this non-spontaneous region up here. Eventually, at this temperature, you will see a crossover where the entropy starts to dominate and the process becomes spontaneous. On the other hand, if it's an enthalpy-driven process, enthalpy-driven needs to happen at a low temperature. So this T equals delta H divided by delta S tells you the highest temperature where the reaction is spontaneous. So this T that we can calculate would give us something, this sort of temperature change where we would swap. And basically, whether or not, as we increase the temperature, what we change from either the reaction happening to not happening is dependent on that enthalpy-entropy-driven classification that we saw previously. One quick note if you do this calculation and you get a negative temperature, that is impossible. You cannot have a negative temperature. What that means when you get a negative temperature is that you're dealing with either this situation or this situation. Basically, it's telling you that there is no real life temperature where the spontaneousness changes. It's either always spontaneous at every single temperature or never spontaneous at every single temperature. All right, let's look at an example. Over what temperature range is the following reaction spontaneous? It's the same barium oxide plus carbon dioxide gives us barium carbonate. So we already know this reaction is spontaneous at 298 K. Well, what general temperature range will it be spontaneous? All right, so over what temperature range is the following reaction spontaneous? So I want to know what temperature range is my reaction spontaneous. So I'm going to be looking at, what I'm looking at is changing the spontaneity of a reaction by changing the temperature. Basically, how can I make a reaction tend to happen or not happen? We know if you want to boil water, you heat it up. And so that's where it starts to become spontaneous. So I want to know, can I make this reaction change from being either spontaneous to not spontaneous by heating it up, or the opposite, right? It's not happening, and then all of a sudden it is going to start happening above a temperature. And if we're looking to do those calculations, we can calculate the temperature where the change happens by taking delta H and dividing by delta S. This would tell us, allow us to control when a reaction happens and kind of how and whether or not it'll happen. So it's going to be based around the components of Gibbs free energy. We know this is really all about the Gibbs free energy. This is why we talk about it in terms of the enthalpy and entropy components. So we need to calculate delta S and delta H for this reaction. Barium oxide plus carbon dioxide gives you barium carbonate. So delta S is going to be equal to my products. That's going to be S barium carbonate minus S of barium oxide plus S of CO2. So just looking up those values, barium carbonate is 112. Barium oxide is 72.1. And CO2 is really high, 213, because it's a gas. We put those together. Delta S is going to be equal to negative 173.8 joules per mole Kelvin. So types of calculations we've seen previously. Sticking with it using our tabulated information. So that's delta S. We also want to get delta H. And so it's going to be the same idea, same format, right? Because it's still the same products, same reactants. And so we're just going to go ahead and find those barium carbonate still, negative 1213 kilojoules per mole, plus barium oxide is negative 548. Negative 393.5 kilojoules per mole. Putting those together, you get negative 271.5 kilojoules per mole. This one's, be careful, make sure you can get this number. It's a good thing to practice. You're adding all these negative numbers, just really want to be mindful of doing that arithmetic. Lots of negatives, positives, kind of double negatives canceling out. You want to be careful of. So negative 271.5 kilojoules per mole. Perfect. That's delta H. We got an exothermic reaction, decreases spontaneity, decreases the entropy. Makes sense. We are basically getting rid of a gas, so that number makes sense. And this one, it's harder to predict enthalpy, but one of the things we can see is we're forming like a big compound with lots of atoms in it. Those tend to have strong bonds, so it's not surprising that we got an exothermic reaction here. If you got endothermic on something like this, that's also not crazy too. But we would just, it seems on the up and up. With this one, you can definitely say, like, if we got a positive number here, that makes no sense. You are getting rid of gas. But all in all, looks pretty good. So now we want to combine these in this equation right here. T is going to be delta H divided by delta S. So we got to plug them in now. So the delta H is negative 271.5 kilojoules per mole, and my delta S is negative 173.8 joules per mole Kelvin. Which one of the things we want to be mindful of is I got joules and kilojoules. Those aren't going to work. That's not going to cancel out correctly. So just like we saw when we were doing delta S of the universe, we need to make sure that these two components have the same units. It's the same exact issue we saw previously. It's a common kind of concern and a problem that we would be facing. And so we could see that basically this, what we'd want instead is basically turn this into joules. So negative 271,500 joules per mole divided by negative 173.8 joules per mole Kelvin. And I'm gonna, if I plug that in, I get that T is equal to 1,562 Kelvin. So this tells us the temperature where the spontaneousness of the reaction changes. It doesn't tell us how it changes in terms of below or above this temperature, which range is the process spontaneous, just that it will be, this is where it changes. That's what we're figuring out here. So there's a couple things we want to, ways we want to modify this. First off, this temperature is in Kelvin. That's not functionally that useful. Most people do not think in Kelvin temperatures. So we want to convert it into a more common temperature that we use in terms of controlling reactions and reaction temperatures to be Celsius. So really what we'd want is the temperature is equal to 1,562 Kelvin minus 273, which is going to be equal to 1,562 minus 273 is equal to 1,289 degrees Celsius. So that's a pretty high temperature. So it certainly is a very high temperature. And so that still only gives us a temperature change, or where the kind of properties change. So we still want to get some, kind of slightly better information, and that would be what we're really looking for is a temperature range. Not just the temperature where it changes, but what side of this is the reaction spontaneous. And in order to figure that out, we need to look to, is this enthalpy driven or entropy driven? And so we saw that previously, it's based off the sign of delta H and delta S. So very nicely here, we can see that these are both negatives. Both negatives imply that it is enthalpy driven. So we could use that delta H is less than 0 and delta S is less than 0. Those combined tell you that it is enthalpy driven. And so we could know then that that means that if you want to remember, enthalpy driven means this is the highest temperature. The other way you can know is that these are both negatives. So they imply below. So this reaction is spontaneous below this temperature. So reaction is spontaneous below 1,289 degrees Celsius. So if you want to run this chemical reaction, you just need to keep your temperature below that very, very high temperature. Above that temperature, it's not happening. Above that temperature, it is not a spontaneous process. But as long as you stay below that temperature, where the enthalpy is more important at low temperatures, the enthalpy-driven aspect of the reaction can happen. Once you raise up the temperature, entropy becomes more important, and that's not happy here. So that's why the reaction wouldn't happen. But the reaction is going to be spontaneous below this temperature. So you got to figure out the temperature, and then you got to figure out is it enthalpy or entropy driven, or just look at the signs here, and you get that. One quick note, this temperatures in Kelvin, you better not be getting negative temperatures in Kelvin. Either that means you cannot change the spontaneousness by changing the temperature, or it means you may have made a mistake. So important to kind of look at and consider, but we are not expecting negative Ks, negative Ts, because you can't have negative Kelvin temperatures. So the temperatures you're going to get out are always in Kelvin. So anywhere below 1,289 degrees Celsius, this reaction is going to be spontaneous. And so that really means that if you're trying to do this chemical reaction, you have a lot of flexibility. You could really heat it up, say you're trying to speed up the kinetics or something. You have a lot of flexibility to get this reaction to go, and you really don't have to worry about, if you're trying to make the reaction happen, it getting too hot or something like that. You could really crank it. Other things are going to start happening before this reaction stops being spontaneous. But another thing we want to be mindful of is sometimes we don't want this chemical reaction to happen. Like, say you want to have just a sample of barium oxide. Barium oxide will react with carbon dioxide that's in the air. This reaction is spontaneous at not only room temperature, but plenty of elevated temperatures. If you are storing barium oxide, you probably want it to stay barium oxide, meaning you need to be mindful that this reaction can happen. One kind of easy solution is put a lid on your container of barium oxide. Don't let it be exposed to a ton of carbon dioxide that's out in the air. The kinetics for this reaction are probably going to be pretty slow, so you don't have to go too crazy. But, you know, that's why we store all of our chemicals in sealed containers, not just like in piles in the stockroom or all around in like open beakers. You put a lid on it. You know, again, it's not that you need to be so concerned that this reaction is going to be so crazy fast. There's not a ton of CO2 in the air as it is, but you do want to be mindful. Maybe you don't store your barium oxide next to some exhaust on something that's, say, increasing the concentration of CO2 locally, or anything like that. And so you do just need to be mindful that if you allow this reaction to occur, i.e. the reactants can combine together, there can be collisions between those reactants, then the reaction can and will happen. And so we just need to be mindful of that. And these sorts of calculations let us be aware of how we need to be concerned about what reactions can and may happen. Participation 327, question 2. What is the boiling point of TiCl4? That's TiCl4 liquid becoming a gas. There's a table of thermodynamic properties to help you answer that question. This is the second question on participation 327, due Friday, March 27th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the boiling point of TiCl4? I know you can look it up, but you can also use this table of information to calculate it. And probably be really good for you if you know how to do that. Actually manually calculate it using the reference information. So when we talk about controlling, you know, spontaneity, this is something that really is useful, that lets us understand how we can make chemical reactions happen, right? We can determine what sort of conditions we need if we want a chemical reaction to happen, or what conditions we need to avoid if we don't want a chemical reaction to happen. And so one thing we want to discuss is, what about those chemical reactions where delta H was positive and delta S was negative? We said before that there was nothing you could do, there was no temperature change that you could do to make that reaction spontaneous. The thing is, those reactions exist. For example, graphite carbon turning into diamond carbon. Okay, so based on our reference data, delta H, delta S, if you look those up, you are never going to get at any temperature graphite turning into diamond. But diamond exists. So since diamond exists, there has to be a way to accomplish this chemical reaction, to accomplish this transformation. So how do you do it? You don't change the temperature, you change the pressure. So one of the things you want to remember is that all of this tabulated reference information only applies at a pressure of 1 bar. The reason why we use this so frequently in chemistry is that's about air pressure. Most chemical reactions that we do in the lab, we do under atmospheric pressure or 1 bar. But if you go to the middle of the Earth, the pressure gets much higher, and that's the secret to how diamond forms. That's why diamond is found really deep underground, because that's where the pressures are high enough that you can start to change the equations for the delta H. The delta H basically just changes sign, and that is what informs how you get this to occur. And so that is, what we're kind of looking at here. There are these other kind of variables and kind of factors that we can control that we generally don't control in the chemistry lab. But if you need to, you could. And if you find yourself needing to do a chemical reaction with this setup, it's endothermic and entropy decreases. The solution is you got to change the pressure if you need that chemical reaction to occur. All right, we had a participation question in this video. Got a couple more videos left on this set. I'll see you looking for more participation questions. I'll see you in the next video.